I'm Dan. I'm a software engineer at Bloomberg, and I'm a Java and the JVM Guild lead. So in my day job, we get the opportunity to explore interests we may have, especially when those interests align with products and tools that we build. And as a part of my work, I was able to come here to EclipseCon last year, where I met people like Scott, people like Shelly, and I got really interested in both supply chain security and the Temurin build of the JDK. And as a part of this, I decided to get involved in some open source, and this was a really great place to get involved. And this year I'm going to present the project that Shelly kind of assigned me last year. So this is a great opportunity to come full circle. And I'm going to present to you today what's lurking in your JDK, identifying vulnerabilities in Eclipse Temurin. If you're at the virtual Adoptium Summit, this is like a longer version of that talk, where we're not only going to talk about what a vulnerability disclosure report is, but also what it contains and how we built it. So let's start with supply chain security. I'm sure you're going to see a ton of variations of this slide. I've already seen a few today, but software is only as secure as the components that go into it, and software can be exploited if there are vulnerabilities inside. So if you've got vulnerabilities in your components that you use in your software, people can use those to exploit the software that you've built. And the vulnerabilities can either be in the software that you've written yourself, or of course in the libraries used by your software. And by understanding what components go into the software we use, we can understand, and then we can also mitigate the threats. So the other part of the coin, as you may have learned if you went to the session this morning, is that new regulations like the CRA and DORA increasingly mandate that both commercial and open source software are secured at the source. So with that being said, software vulnerabilities. Software might have vulnerabilities, and they can be exploited to produce unwanted behaviors in software. So you can get your vulnerabilities in a whole bunch of different ways. You can get them accidentally. You can get them deliberately through code changes, as we saw with that XZ exploit. You can get them through the supply chain by using vulnerable libraries, and you can also get them during the build and deployment process. Again, this is kind of where that XZUtils comes in, where somebody injected the vulnerability or was able to actually unpack it and use it in the build process. And these vulnerabilities are cataloged by the National Institute of Standards and Technology, which is an agency of the US Department of Commerce, which is, of course, an agency of the US government. And they're cataloged for a couple different things: behavior, affected components, and severity. And that catalog results in the CVE system. And vulnerabilities in libraries and infrastructure can affect anything that depends on the vulnerable component. So for us in the Java world, if our JDK is vulnerable, pretty much everything we build and run on the JDK can also be vulnerable. So it's very important that we have a secure source of information. So we have this idea of a software bill of materials. So I do quite enjoy a bit of food. And here we have a bit of food. It's a cake, right? And the cake has a couple different ingredients. It's got some flour in it, it's got some milk, and it's got some eggs. And if any of these is poisoned, then the whole cake will end up being poisoned. And that's generally not good for eaters of cake. So what we want to do is we want to list the ingredients, right, which is what the software bill of material does. And software bill of materials is typically specified in a standard format, like CycloneDX. In the case of Eclipse Temurin, it certainly is CycloneDX. This is an open source format. It is machine readable, so you can get it in JSON and XML. I think most people prefer JSON. And it contains a list of libraries, versions, and checksums, and it can also contain additional information like build details, anything really that you need to know in order to understand what went into the software. And new regulations require that the producers of software effectively generate SBOMs and identify vulnerabilities in their software. So the vulnerability disclosure report builds on top of that SBOM concept. Matter of fact, in the CycloneDX standard, a VDR is a subclass of SBOM, right? So it has to pass all the SBOM validations and more. And what it contains, it's basically, if that SBOM was your ingredients list, the VDR is the list of allergens, right? It gets closer to that desire of the end consumer to know what they're being exposed to if they're using your software, right? So instead of going, okay, these are all the ingredients of my software, and then forcing somebody to parse through that and go, well, would that version of that library have a vulnerability? With a VDR, you flip it and you say, here are the known vulnerabilities in my software. So it's a lot more user-friendly than just an SBOM. So it lists the known vulnerabilities in the software. It's basically a similar format. You use the SBOM library. CycloneDX is great. They not only provide the standards for the format, they provide libraries. We use the Python library to generate the VDR. And it lists the vulnerability details, the affected versions, and the recommended fixes. And it basically helps software users understand what risk they're exposed to and how to mitigate that risk. Generally, the mitigation is as simple as you're on an old version, somebody found a vulnerability in the library, somebody went and fixed that vulnerability in the library. What you've got to do is you've got to upgrade, and by upgrading, you get the latest version. This is why tools like Dependabot are so great, because tools like Dependabot effectively go, hey, there's a vulnerability in your library. And as a library owner, you want to make sure all your dependencies are up to date, because if you provide somebody a library, of course, any vulnerability in your dependencies is a vulnerability for your clients. So it's your responsibility to publish new versions when a vulnerability has been detected downstream. Even more true for the JDK. So the VDR, basically, we generate this VDR for Eclipse Temurin. We start over here, right? There is this group called the OpenJDK Vulnerability Group. And this group produces a report. I believe it's every approximately 3 months with the new JDK release. And it says, here's all the vulnerabilities we found in prior versions, and we fixed them. And basically, this contains CVEs. The problem is this is a website I'll show you later. So we have to parse that and turn that into a machine-readable representation. Then we have to get some other information about those CVEs, like the description, the affected components, things like that. And we get those from the NIST database currently. We have a current open issue, if anyone would like to contribute, to actually use dependency track, which queries the NIST database among others. And then we try to enhance, the CVs with the information from NIST, and we have one amalgamation of vulnerability data that we pass through the CycloneDX library, and then we generate the VDR. So that was basically the summary of what you're going to see in this talk, is that pipeline and what all the challenges were at all the steps. And currently there's one VDR for all the versions of Temurin. So basically we parse through all the OJVG reports through history, and then we create one VDR, and in the VDR we mention which version of Temurin was affected. So for our pipeline, the step number one is to source data. Now there could be multiple different sources of data. Another open issue in our VDR is to use the Temurin SBOM and run that through the this dependency track tool to generate a vulnerability disclosure report. But currently we start with the OJVG's trusted quarterly reports. So basically you have an example here. This is a web page, right? And what we do is we download this web page, and this web page shows you the CVE ID for each vulnerability, right? And then it shows you the affected components. It gives you a CSS score, right? This is the severity. This goes from like 1 to 10. 1 is not dangerous at all. 10 is absolutely critical vulnerability. And this is important to have from here, because actually, depending on how you use your severity score, it might differ between what the OJVG thinks and what NIST thinks, because NIST analyzes the library kind of holistically in all its possible usages. But that vulnerability might not actually be used in the OpenJDK, so the severity from OJVG might be lower, because we might not be affected by the vulnerability in the library if we don't use the code path that exposes it. So we take this web page, we parse it out using the Beautiful Soup Python library. The first challenge is this kind of a listing of the report dates. I know it's very small, but basically they're 3 months apart, 4 times a year, follows the OpenJDK release cycle, but they're not on the same exact date. So figuring out when the next one is going to be is an imprecise activity, at least according to the Gregorian calendar. So Initially, I started on the earliest day and was downloading every day and seeing if I was actually getting a web page or getting like an error 404 not found for each of the days, but that was a lot of downloads. So now what I've done is I've hard-coded the list up to the present day, and then we'll scan forward from the present day so the tool keeps getting vulnerabilities. And then once in a while, we update the code to have that list up to a certain day and increment the present day, which is the last known vulnerability report, so that we're always scanning in the future every day, but in the past we only get the known vulnerability report days. And we're guessing basically they're never going to publish a retroactive vulnerability disclosure on a different date. And the URL basically contains the date, so that's kind of how we download them. So the other challenge that we face with this is it's formulaic, but not exactly the same. So we were using some keywords, right? You see it's very small text, but you might see here that it says, the affected versions are 22, 21.0.2, 17.0.10, 11.0.22, and 8U402. And in the previous one, it starts, after that it says, we recommend that. And afterwards it says, please note that. So we were using that next sentence to basically figure out where the end of vulnerabilities was, and we had to basically code for 2 different variants. And before doing that, we were not getting these affected versions. The other challenge here is that basically you can see that we get the major and minor versions up here, and then we only get major versions on the CVE risk matrix. So if there were ever 2 minor versions for the same major version that were affected, and then 2 CVEs that were talking about that major version, it would be impossible to distinguish whether both minor versions affected both CVEs or one affected one affected the other. At the moment, what we do is we assume the worst, right? So if you've got 2 minor versions for the same major version up there and then 2 CVEs for the same major version below, we just assume that both minor versions are affected by both CVEs. The end goal, though, is to talk to the OJVG people and get them to give us machine-readable reports, because this would make our lives a lot easier. We could get rid of these ambiguities. Of course, if you're parsing out a JSON, you've got JSON parser libraries. You don't have to depend on key phrases. So that's how we get our source information. Again, we have an open issue if anyone wants to contribute, where we can try to build our own SBOM-based VDR using that dependency track library. And that would effectively look through the SBOM, find vulnerabilities, but the OJVG one is kind of a very trusted source. It's not very noisy, so it's a very good place to start with a VDR because it has a high trust factor. So yeah, this is that affected versions. I forgot how to slide on it, but basically you can see that we use the risk matrix combined with the affected versions to guess which minor versions are affected by which CVE. The other challenge we actually face is that we're talking here about OpenJDK versions. There's no way to actually cross-check this with the NIST database, because NIST will say, this is Oracle JDK version X or some other JDK build version, which might not necessarily correspond one-to-one with the OpenJDK version. And the other challenge we actually face when it comes to JDK versions is that we currently don't have a PURL standard for the OpenJDK to say the OpenJDK Perl for the affected version is X. So we're doing our best, but this is where we could use some help from the standards. There was a talk earlier from one of the people responsible for Perl mentioning that they're building a top-level Apache Software Foundation Perl repository. So if we get one of those for Eclipse, we can then get a sub-component for Temurin, and that would be really great. So after we have retrieved those vulnerabilities from the Open Java JDK vulnerability group, we need to get additional information like the description, the additional severity score, and links to external analysis from the NIST database. So we query the NIST database for each CVE, and the final vulnerability information is compiled into one record for each vulnerability, which we then pass through that CycloneDX library to create the final VDR. The NIST challenge we have is API throttling. So it's got a free version and a premium version. The free version has a rate limit. The good news is we have an API key. The bad news is if you're running this in a PR in GitHub Actions very reasonably does not allow you to have your secrets exposed, because then people could just print them and find out all your secrets, and that would be bad. So basically you don't get environment variables in GitHub Actions with the API key. So the good news is that the free API is the same as the premium one, it just has a rate limit. So the solution is basically I've throttled the thing to stay within that rate limit. The downside is it takes half an hour. We do have an open action item to actually use dependency track to, because it has a cache basically of the NIST database. So we could, if we use the Dockerized version of dependency track or the GitHub Actions version of the dependency track, we could query that as quickly as we want to and generate the report quickly instead of slowly. So great, we've asked the OJVG what the vulnerabilities are, and then we've basically downloaded them, parsed them, we've asked NIST what it knows about those CVEs. What we have to do now is export. So CycloneDX is the standard bearer. We use CycloneDX because everyone uses CycloneDX, and that means we're interoperable with existing tools. If new tools are built to the CycloneDX standard, you can use them with our VDR. Great. So, of course, being JSON and XML, every language under the sun has a JSON parser, which is great because you can analyze it however you see fit. And they have a Python library. So basically, our thought was, if we use the CycloneDX Python library, then we should just be generating a valid report from the start, right? There should be no need to adapt it. Almost true. And the great news is the final report can then be linked from versions of the Temurin release so that users of Temurin can be aware of what vulnerabilities exist in their versions and what the remediation plan is. That's still an open action item to pick up the report from the GitHub Actions and put it in the API if anyone's interested in helping out with that. So the challenge we faced was we were creating this VDR, we were all excited, it was great, and then somebody pointed out that there is a validator tool for SBOMs. So I took it and I uploaded it to the validator tool and it said invalid, and that was bad news. So it turns out that the CycloneDX Python library, because I didn't have type checking turned on, was being very permissive. And it was generating a JSON report, but it wasn't passing the validator. So I opened an issue in the libraries repository. The community was great, replied really quickly of, hey, you need to actually install this extra validation component of the library using pip. And you need to use mypy to type check. And once you do those things, you should generate a valid one. So I did these things. And I was able to get a valid VDR, which passed the external CycloneDX validation tool, which I believe is written in Golang. So great, we now have a valid VDR, which is better than an invalid VDR. And the way we generate the VDR, this was actually my first experience working with GitHub Actions, because internally we use other tooling, some of it based on Jenkins. And I think it's really worth, if you haven't used GitHub Actions, to try GitHub Actions, because it's really good to work with. It lives in .github/workflows in your repository, right? So it's just another directory in your repository. And that means that basically your CI, your build process is just as open source as your software, assuming your software is open source, right? It all lives in one place, and that makes it really easy for discoverability. A GitHub action has a name, right? It can, each file in .github/workflows will have the name of the GitHub action, and it also contains it in the JSON, oops, up there. And it can be triggered either automatically, manually, on pull requests, on branch pushes. It's got all sorts of configuration. We generate a VDR every time you update your pull request so that you can see what the output of the VDR generation would be. It runs on a base image. We use Ubuntu latest. Seems sane enough. And it basically, a GitHub action is a sequence of jobs, right? So basically we have a bunch here. You can see basically we install Python, we install our dependencies, we download, then these are the last few are kind of the ones that I've written myself. download OJVG, this is basically where we're able to, we call into the library that I've written, and that downloads the vulnerability disclosures from the OpenJDK vulnerability group and parses them. And then we run the convert. So then we turn those into a VDR and call NIST. So you can basically run all your commands. And the other great thing that GitHub Actions does is it has this action, right? So GitHub Actions it's basically a composable sequence of steps. And one of the steps that's provided for free by GitHub is the ability to upload a directory. So we upload the data directory, so all the things that we downloaded, we upload, which means that the user, the person who opened the pull request, can introspect whatever you've uploaded. So in this case, every web page we download from OJVG and every call we make to NIST, we save this in a directory so that for debugging purposes, the user can go and figure out, okay, I did get this data, this is the web page I got, I can try to reproduce locally why I wasn't able to parse out vulnerabilities from that web page or something like this. And you can basically, because you have full visibility, you can debug your stuff without rerunning CI. And then we also do a final upload of just the VDR because some people will be interested in just the VDR without the intermediate data that's represented. So GitHub Actions are great for a few different reasons. One, it's trusted infrastructure, right? It runs on GitHub servers, so if you're looking at a brand new project, you don't have to trust that some person set up their server correctly. You're more likely to trust that GitHub, and by extension Microsoft, has done the due diligence and set up a pretty secure environment. And if they haven't, somebody will have figured it out and they'll have hopefully patched it really quickly. So, and the other great thing is, of course, because it runs on GitHub servers, if you fork it, you should be able to reproduce the output fairly easily. It's also, it makes your CI/CD steps open source, and I think that's great. It means that it's not just it's just code in the repo, right? The CI is simply code in the same repository, so it's accessible to anyone that can see the repo. This kind of makes your setup for doing CI/CD completely discoverable. The other thing is there's no DSL. So Jenkins, for example, uses Groovy, so you have to learn Groovy and you have to figure out how to integrate Groovy with the stuff you're doing. This is simply a YAML. YAML's pretty easy to understand, and then everything else is just shell script that you can run. So I think the learning curve is very, very easy to get past. It's got super powerful built-ins, right? Like, it's got existing GitHub Actions to do running a build system, linting, uploading artifacts, so all that stuff is built in, and it gives you more confidence. It gave me more confidence that I was just able to use the existing Python 10, 3.10 or whatever, GitHub Actions, right, to run the linting, run the tests, rather than roll my own, because since I'm using the existing one, it means I must be following something close enough to best practices, right? So the less code I write for my CI, the more I use the standards, the more likely it is that other people will be able to pick up that repo and just start developing on it. And the other GitHub value add is Dependabot, of course, which keeps your dependencies up to date and secure, and it runs as a GitHub action. There was a great talk earlier. I believe there's another one called Renovate, which is fully open source, but I believe that's also available as a GitHub action. So you're tied into that rich ecosystem. A lot of open sources on GitHub, and a lot of these tooling, even a dependency track, is available as GitHub Actions. So all the best tools tend to be available. So the final report is generated using GitHub Actions in that secure environment provided by GitHub. Users can view the logs in the output. We create a VDR on every PR. It's transparent generation, right? As I said, you can introspect everything in that data directory to see what source data we used and correlate that to the output VDR that we created. This is both great for bugs, and also if you don't trust it, you can introspect it. And it's rather small, but you can see kind of here's a bit of a sample bit of the VDR. You can see that we have a vulnerability here. The first one, for example, it's got an ID, it's got a description that it says it's a vulnerability in the Java SE component, subcomponent 2D. It's got the affected versions in the description. It's a difficult to exploit vulnerability that allows an unauthenticated attacker with network access, whatever. So that's that thing. It tells us that the CVSS score actually matches from NIST and from the OJVG, and it basically tells us the date it was published, and then we also get the affected versions somewhere in here. Yeah, so you can see down here you've got an effects 11.0.37 U221 8 U212. So that's kind of what a final vulnerability looks like in the VDR. So if you have the VDR, you can tell if you're using those versions, then you're affected by the following vulnerabilities, and you can do an impact analysis and hopefully upgrade. So what's next? As I've mentioned a few times, we'd love to integrate the Temurin SBOM and scan components in Temurin's SBOMs to the vulnerabilities and add them to the VDR if they're critical enough. We might try to leverage dependency track to do that for us automatically. The challenge we might face here is it might be a bit noisy, and we'll have to come up with good ways to detect which vulnerabilities are real and which are false positives. In terms of ease of consumption, we'd like to link it from the Temurin releases and make it available via some kind of API. And we'd like to improve the pipeline, right? So a big part of this would be working with the OJVG to get them to produce machine-readable reports, and then to use that dependency track instead of the NIST API, because both it has higher throughput, and if the dependency track people are able to integrate vulnerability information from more sources, we'll get that for free as well. So thank you so much. If you'd like to contribute, that's the URL. And on Slack, we're the secure dev channel in Adoptium. If you have any questions. Yes. So the question is, I'll repeat, I'm not sure if the video catches without the microphone, but the question was, we produce kind of an aggregate SBOM for all of Temurin. Is there any plan to generate component-specific SBOMs and VDRs? Is that inaccurate? So I think with Temurin, because it's the JDK, you're using kind of the whole JDK. I guess you could say some of the libraries might have vulnerabilities like whatever, Java util, or some, I'm assuming probably the networking stuff would be more likely to have a vulnerability that's exploitable. I think right now we don't necessarily have, at least I'm not aware of any plans to do per component SBOMs, but if we get our affected components right in the whole VDR, it should be as simple as filtering the whole VDR for the components you're interested in. I think that could be an approach. I think we're also kind of here because we are using very high level information from OJVG itself, right? The granularity we have is the granularity they give us. Once we start moving to the SBOM, right, this is theoretically a fairly generic VDR enhancement pipeline. So like whatever vulnerability you might be aware of, you can pass it through, enrich it from other sources. But I think for us, the secret sauce here is that OJVG high level, these are the actually important vulnerabilities. So it would be a question of, you know, there's kind of course, the two approaches. One is to get an SBOM and try to generate a VDR out of it. And the other one is to trust somebody that's curated your vulnerabilities. And if that somebody that's curated the vulnerabilities doesn't give you component level information, although I guess they always tell you an affected component, right? Then we don't have a per component SBOM per se, but you can always filter it. Does that help? Yes. Mm-hmm. So the question is how do you avoid doing a commit to get the GitHub Actions to run? For me, the answer was, with Python, it was quite simple, right? It's it just does the linter and the PyTest, so if it doesn't pass the linter and the PyTest locally, I don't even bother committing it. Or, I mean, I'll commit but not push or something. And the other stuff for when it's running my pipelines, right, those are just 2 simple Python 3 command invocations. And I try to do all of my development such that it must build locally first, and it must not stop building locally. And I think in the Java world, it's even easier, right? Because your Maven stuff should just all, or Gradle stuff should just all work locally. So I think in my mind, the approach that's always worked best is to start local, make sure it never breaks locally. And then because you're able to write shell script, you can always have kind of an action that's just do whatever you need to do in a shell script and make sure that shell script is also working locally. I think that's my general approach. And it works with even things like Jenkins, right? Because even in Jenkins, you can call a shell script. I think the more you make sure that the stuff just works in a standard Unix environment, the easier time you have. Cool. Any other questions? In that case, thank you so much for coming. Please consider consuming, please consider contributing, and as always, make sure that you're using Adoptium Temurin.